This is 23.2, Applications of Circuits. Today we're going to just talk a little bit about circuit safety, and then we're going to get to those complex DC circuits. Where are you working a second ago and not working today? Come on. All right, so first of all, when we talk about safety with circuits, we're trying to prevent a short circuit. A short circuit happens when you have a really high current and a really low resistance. That means that the electrons, there's a lot of electrons moving past on the wire very, very fast because they have very low resistance. So when this happens, the wire heats up so much that it melts the insulation, and the wire's insulation usually catches on fire. This is what happens in a short circuit. So when we're talking about safety, we're trying to prevent these.
Is a short circuit like when you have your phone on the charger and the charger gets like really hot?
Well, a short circuit would actually affect hot on fire. Like melted the wire. But this is what's happening. It's just not a short circuit yet.
Is that like those things in the outlets in bathrooms, like in case of like an electrical problem and like?
Well, the short circuit is what you're trying to prevent from happening. That's a circuit breaker.
Oh, so that's like.
It's like a little switch,
Oh.
and it turns off the circuit, which I'll show you in a second. Actually, I have them back there too in the lab areas. There's on the left side, from my point of view, there's like a little tiny button. And sometimes if I put too many of the hot plates on high, it pops them off. All right, so one of the things that we put in there to avoid that is a fuse. Now, I'm sure you've heard of a fuse, even though you don't know maybe what it is. It's just a piece of wire that melts before the rest of the wire does. And so when it starts to get a really high current, that piece of wire will melt and break the circuit. So a lot of times, if you're the person that usually does the Christmas lights in the family, I was always that person, you'll get these in little packages. You get like the two little metals with the clear. That's just like a little piece of wire in there. And you can put them in your Christmas lights. And that's supposed to keep your Christmas lights from getting really high current and lighting your tree on fire. That avoids that. Did you know you also have fuses in your car? Most of the fuses in your car, if you open up the driver's side door and there's like a panel right on the steering part of your console, there's some fuses in there. And there's, I'm sure there's fuses other places in the car. That's the only part I know about. And I know some houses have fuses in them, but most of them are circuit breakers now. All right, a circuit breaker is just a switch. It measures, it's detecting how much current's going through, and it has like a limit, and when that current gets too high, it just switches off. So this happens if you're running like the microwave and toaster and the vacuum all in the same room. And it's usually by room, your circuit breakers are by room, so you just go to the garage, you open up the circuit breaker panel and flip that one back on, make sure you don't run the microwave, the toaster, and the vacuum all at the same time. Now, to prevent that, all you have to do is plug the vacuum into a different room, and it should be fine. So it's just a little switch, and it turns off, and it breaks that circuit so no more current can flow. Okay, are you guys ready for combination circuits? I've been building up to it all week. You thought series was easy. You thought the parallel was easy. Now, we're going to combine them and show you that two easy things do not make another easy thing. They make a very hard thing. So this one up here is a combined circuit. We have series and parallel. This one is in parallel. And if we take these two, we know they're in parallel because we got a junction between each one. And if we take these two and combine them together, so we take resistor B and we take resistor C, and we smash them together using the parallel rules. So we'd add them up inversely. 1 over RB plus 1 over RC will give us 1 over RBC. So we're going to take these two and smash them together. And then we get a nice simple series circuit and we just solve it like normal. So the idea with complex circuits is to smash what you can, like the resistors, together to make them simpler and simpler and simpler until they look like one single circuit. Usually what you want to do is start at the most complicated place furthest away from the battery and then simplify and simplify until you get to the battery. Okay, so in this one, furthest away from the battery, we have a nice little parallel series. We have a junction and a junction. If we smash these two together, then we get a nice simple series circuit, and we can solve. Okay, so let's try one. Yeah, I will when we do it. How come the down? Okay, so here's another one. You can see that furthest away from the battery, this one's in series because even though there's a junction here and a junction here, there's still one wire between each one of these. So it's automatically a series. As soon as you have one wire between circuits, then it's a series. So even though there's a junction here and a junction here, these ones can be solved in series. So we'll combine these into one single series. So it'd be like R1 plus R2 plus R3 gives us one single resistor. And then it's in parallel with this one, so then we solve it like parallel. You could not do the parallel first because it's these ones are connected together. So it wouldn't be like parallel with this one and this one, parallel with this one. You have to do it all at once. Okay, so let's look at this one. We've got the left side, we've got the right side. What will we do first? The series on the right. Okay, so we're going to combine these three together. Let me redraw this, make it a little bit easier for us. Here's what we got. So we're saying combine these ones together first. So we smash that all the way down into one single resistor. I'm going to redraw it. So this is our three that are smashed together. Now what will we solve? The parallel. Good. So this section right here. So that would be, then we'd just be left like this. That's our combined circuit. So this one's the one that's all smashed together. So this one's these three smashed together, and this one is all this stuff smashed into one single spot. So then we can just solve it like a series circuit. Okay, so this is the one that we're going to practice today, and it will probably take me a good 15 or 20 minutes to solve. And I'm happy to answer your questions. I just need to change out my pen real quick. Okay, so let's also a new page. Erase this. The first thing I like to do is to draw the circuits. So redraw. And again, you can label these resistors anything you want. Could be 1 through 5 like it is up here. It could be A through B. It could be in any order. It doesn't matter. You can call them Bob and Sally, just as long as they have some sort of label so we can refer to them. I'm going to stick to what's up here, 1, 2, 3, 4, and 5, just to be consistent here. And this is a 5. Now, if we're smashing together our circuit to make it a little bit more simple, what resistors, and I've already numbered them, so you can tell me their numbers, would we smash together first to simplify? 4 and 5, good. So if we redraw, it would look like this. 1, 3, 2, 4, 5 together. Okay, now what will we solve? 3, 4, 5. Good. So we combine these ones together, and we'd end up with a nice little circuit here. And this would be 3, 4, 5, 1, and 2. Now, sometimes when we start doing this 3, 4, 5, it ends up being like 3, 4, 5, 6, 7, 8, 9, 10, or however many resistors we have. If it's easier, you just want to name it something different, like RA, or I think in my homework you'll see me go RS1 or RS2 for Series 1 or Series 2. You can label them whatever you want to make that shorter if you'd like. If you'd like to just stick with the numbers, that is okay too. Okay, now that we've got this simplified, I'm going to show you how to use it. We're going to draw the grid. Burp. And we've got 5 resistors, so we need 6 columns. And I'm going to plug in what we know, what's given in the picture. We have R1 is 220. R2 is 130, R3 is 470, R4 is 100, and R5 is 270, and it says that the battery is 18 volts. So everything that is up on that screen is now on our board, or on our paper. We don't even need to look at it. Hello? Sure. Chris, you're checking out. Okay, normally in either a series or a parallel, you would say, oh, it's series. If it's series, I'm going to add up all these resistances and boom, get my total resistance. Or if it's parallel and add them up inversely, I get my total resistance and then work on my way back. You can't do that here. Doesn't work. Instead, because we have to smash together certain resistors, some in series, some in parallel, it'll be a little bit different. All right. Are you guys ready? Let's see what we got then. Okay. We need to work this way, and then we're going to work our way back. So we're going to start with resistances. We're going to combine 4 and 5, right? We have to find R4, 5. Now, R4, 5 is in series. So R4, 5 should just be R4 plus R5 because it's in series. Why is it series? Because there's one line between 4 and 5. So even though there's junctions over here, we have at least one spot where there's one wire between them. Yes?
So you're saying that if it was like 4 and then it made a line and then it was another.
Yeah, if it was like 4, 6, 5, yeah,
That's still
you'd be
series.
4, 5, 6. Or if you had 10 of them here, you'd add 1 through 10 up because they all have one wire between them, so they're all series.
So one of them would be parallel.
What's the next one? So let's solve this one first. We've got R4, R5. We know the numbers for 4 and 5. R4, 5 equals 100 plus 270. So this R4, 5 is going to be 370. And I'm just going to write this up here. R4, 5 equals 370. Questions yet? Okay. So the next part is we combined R3, 4, 5 because they're in parallel here. See how they're parallel? They've got a junction here, junction here. There's no single wire that's connecting them, just junctions. So this one's in parallel. Since it's in parallel, in order to find R3, 4, 5, you have to add it up inversely. So it's going to be 1 over R3 plus 1 over R4, 5. So R3 is right here, 470. And R4, 5 we just found to be 370. So R3, 4, 5 is equal to 207. Questions? Questions? We're all okay? I'm not going to murder me yet? Okay. Now, you need to remember to solve for the rest of this stuff a couple of rules. One is ver, right? Threshing is cold. And the other one's piv, which the new one is poison ivy, right? Equals ivy. All right, and then we have for series, our rules are R is added, I is constant, and B is added. For parallel, R is added inversely, I is added, and B is constant. Okay. That's all you need for this whole piece of paper that I gave you for home. All right. So we did, this one was series, this one's parallel. What's this one? Series. This will help us find our total. So our total, since it's in series, R is just added. It's going to be R3, 4, 5 plus R1 plus R2. We got bang, bang, boom. So our total is going to equal R3, 4, 5, which we just found to be 207, plus R1, which is 220, plus R3, which is 470. You might want to double check my math in case I get it wrong.
This one's 130.
130. Okay. Where did I get the 470 from? Oh, I was looking at R3. There we go. 207 plus 220. 557. See what happens when I get phone calls and I have to whole groove is just going. Okay, 557. So that's our total. That's here, 557. Now what's nice about this grid is as soon as you get 2 in one column, you can just use VER and PIV to figure out the rest of them. So that should be our goal for the rest of this on the way back. So using VER, let's find our total. We have V total equals I total, R total. So V total is 18, I total is what we're looking for, and R total is this 557. So 18 over 557. Now your currents tend to be pretty small numbers, so that's okay when you get 0.032.
Is this for the entire thing, or is this just for the parallel? Just this grid?
No, the grid is going to be for the whole thing.
Well, then where are you incorporating the parallel?
I'm going to get that. Okay, so now this is where everybody struggles. We're halfway there, by the way. I know we've only filled out 2 numbers in the table, but we're halfway there. So we've worked from the most complicated stuff all the way down to this nice simplified circuit finding our resistance. Now, using these rules and VER, we're going to work our way back up, finding V and I as we go. And that all comes to, is it series, is it parallel? So in series, what's constant? I is constant. So I is constant. That means that this 0.032 is going to be for I1, I2, and I3, 4, 5, because they're all in series. So I'm just going to state that right here. I total, because it's series, means I1 equals I2 equals I3, 4, 5 together. So I can put that in here, 0.032, 0.032. Now I have R, 3, 4, 5, and now I have I, 3, 4, 5. Because it told me that right there. So I have R, I can find V. So V, 3, 4, 5 equals I, 3, 4, 5, R, 3, 4, 5. V, 3, 4, 5 is going to equal 0.032 times I345, which we found to be 207. $6.62. Okay, let's go over this one more time. We have R totals. We found R total by doing R1 plus R2 plus R3, 4, 5 because they're all in series and in series R is added. We found our R total. Then we have 2 in the column. We can use VER, V equals IR. V was 18, R was 557. We were able to find I. It's this part right here. Then, because they're all in series, I is constant. So the I that we just found for the battery is also the I for 1, I for 2, and I for 3, 4, 5. Because I is constant. We have R and I for 3, 4, 5, so we could find V, again using VER. That's where we're at right now. Okay. You guys ready to move this way? Yeah, you guys are ready. Okay, so this 3, 4, 5 represents 3 and 4, 5 together. In parallel, what's constant? V is constant. So if, this is 3, 4, 5. 6.62 represents the whole circuit, then this will be 6.62 for the whole thing. That means that V3 is going to be V345 should equal V3, and it should equal V45. Because they're a constant. So if the whole thing, if this resistor represents both of these smashed together, and the resistor is the voltage is 6.62, that means this is 6.62 and this is 6.62, since V is constant. So that gives me V3 and V45. So now I can find I45. So if V45 equals I45 R45, V45 is 6.62, I45 is what I'm looking for, and R45 is 370. And I get 0.018. So we just solved R45, V45, and I45. That means this section represents 4 and 5 together, this stuff. So in series, what's constant? I is constant. So if the I here is 0.018, then the I here is going to be 0.018. And since they're in series, both R4 and R5 are going to be 0.018. So if I45 is 0.018, so will be I4 and I5. So 0.018, 0.018. And now all the work is done. You guys not believe me? You don't believe me. The rest of it's just ver and pip. As I said before, as soon as you get 2 numbers in a column, and since we have 2 numbers in each column, we can just solve it out nice and easy. I'll do a couple of examples on the board. For the first one, V1 equals I1 R1. So V1 equals 0.032 times 220. V1 is 7.0. And then for this one, you do V divided by R, right? V equals I1. Do that. So 6.62 divided by 470, giving me 0.014. Multiply these two, 0.018 times 100, give me 1.8. Oh, I forgot this one. 0.032 times 130, 4.16. 0.018 times 270, 4.86. So ver to solve for all of these. Right here, ver. How would I find power for each one of these? Pip. So I'll just show you the first one. P1 equals I1. V1. P1 is going to equal 0.032 times 7.04. And I get 0.225. I'm going to do that for the rest of these. 4.16 times 0.032. That's a 3. 6.62 times 0.014. 0.093. 1.8 times 0.018. 0.032. 4.86 times 0.018. 0.07875. And 18 times 0.032. 0.57.